Okay, it's 7 p.m. So let's get started today. So good evening, everyone. Hope everyone's doing well. So it's been a week since we last met. So it's definitely been crazy times. Definitely feels like the situation escalates every single day. So make sure you guys are keeping safe. So the kind of the new thing that's kind of happened ever since last week is that they completely basically shut down the entire university. So even they're telling all the faculty to work from home. So you can tell this is not my office behind me. This is my my apartment. So you can take a look into my my personal life a little bit. Right? So it's, even though it's of course lecturing online is challenging, but there's always a silver lining to things. So the nice thing is I can lecture in my pajamas now, which is really nice. Earlier, my girlfriend came home and she asked me if I was going to put on a nice shirt. And I said no. Why would I do that? I'm in my home right now. So I'm wearing just clothes that are comfortable to me. So hopefully you guys are comfortable as well, right? So the plan for today is we're going to finish up our we had kind of a little bit last time on boundary layers that I wanted to finish up, and then we kind of had part 2 of the boundary layer notes that I posted the notes for this morning. Okay. Before we begin, there was a question before the lecture that I kind of want to make sure that everyone heard, because it's kind of important just for the logistics of the class. So because the university is not letting us come to campus anymore, that's going to make things difficult. For the lectures, we have this Zoom thing kind of figured out, but the exams are going to be more difficult. So we're still going to have our exams. So we still have our second midterm, and we also have our final exam. Okay. And so the way that those are going to work is they're basically going to be take-home exams, right? So midterm 2 and the final exam are going to be take-home. So how that's going to work is that basically at 7 p.m., at least for midterm 2, and then for the final exam, whatever we're supposed to start that, I'm going to open up an assignment on titanium with a PDF that you can download, and then basically you'll download that PDF, and you'll have 24 hours basically to complete that exam and turn it in, the next day, 7 p.m. or whatever the time the next day. Okay. So the time frame for 24 hours, that's mostly given to you guys to give you some flexibility, because I know these times are really challenging, and your health and the health of your loved ones, I think, should take first priority. So if there's a doctor's appointment you got to go to, or family you got to visit, or somewhere you got to move, I wanted to give you guys that flexibility to during that time to basically take care of what you need to take care of and still come back and to be able to do the exam. Right? And that's also kind of why I'm recording these lectures, so that if you can't make it to the real time, you can kind of view them kind of at your leisure. So in terms of the difficulty for the exam, which is probably the question on everyone's mind, I'm kind of undecided right now on if because it's a longer time frame. Usually professors they take that opportunity to make the exam harder. I'm kind of a little bit undecided on that, just because the content for this class is already really difficult, and kind of the point of this class, or at least the way that I see it, is to help prepare you guys for the comprehensive exam. So to have kind of an exam that's kind of pulling stuff way out of left field, where you wouldn't see that stuff, I think is a little bit not as useful to you guys. So I'm still kind of thinking about that and trying to decide kind of what I want to do. So I'll probably have a better answer for you probably either during the spring break or after the spring break. So the question is the exam going to be comprehensive? So for the second midterm, it's not going to be cumulative. So the second midterm is just going to be stuff that we've covered since the first midterm, right? So that was the policy that I kind of put at the beginning of the class. So I plan to stick with that. So I think everything, basically low Reynolds number from before that, you won't have to study for this exam. I mean, some of that stuff will kind of show up just naturally, just like Navier-Stokes and solving for velocities. You should know how to do that, but it's not going to be explicitly on that stuff. But the final exam will be cumulative. So the final exam will have kind of everything, basically from week 1, basically all the way up until the week 15. The difference is that for the final exam is that even though it's going to cover stuff from up to the first midterm, it's not going to be absolutely everything. So for the final exam, what I like to do is I'll make a study guide for you, basically just as I did for the first midterm, and that'll basically tell you kind of what stuff I expect you to know for the final exam. But we'll kind of cross that bridge when we get there. But that's kind of what I had in mind for that. Okay. Okay, are there any questions on just kind of the logistics of the class going forward? I know we had a homework due today, so I had the homework due today on purpose so that you guys wouldn't have anything to work on. So I'll be grading your stuff over the spring break, so there won't be a new assignment until basically when we come back. But are there any questions on the homework before we get started today? Okay, so the question is, can we briefly discuss number 3 on the homework? Sure. Okay, so let me do this. Let me share my screen here. Okay, so problem 3 was a boundary value or boundary layer problem. Okay, so basically, it was a little bit difficult to kind of make this problem because a lot of the stuff we did for boundary layers so far has been mostly theoretical. So a lot of this problem kind of focused mostly on kind of the boundary layer thickness. Okay? So for the geometry of this problem, we have this duct. So into this duct, we have flow. And we say that the flow is basically uniform across this cross section. Okay? And basically, the big design requirement for this duct is that the velocity at the center of the duct has to be basically the same as the free stream. So basically, in the center of the duct, you have to have U infinity is equal to 1. Okay. Because basically what we know is that as the air enters this duct, boundary layers are going to start to form on both the top and the bottom surfaces. And then inside the boundary layer, our velocity is going to be less than 1 centimeter or 1 meter per second. Okay? So with that in mind, basically what you need to do is you needed to use our formula for delta 99, assuming that we have a Blasius boundary layer here. Okay? So kind of at one section of the notes, there was a point where we basically derived the formula for delta 99 for a Blasius boundary layer. Okay? And so for this first part of the problem here, part A, basically what I wanted you to do was to determine the length of this section here, such that the boundary layer basically never reaches the middle of the duct. Okay? And so what I wanted you to do for part A was to take the formula for delta 99 and basically set this equal to basically half the length of this duct. Okay. So if the cross-sectional area here is 25 centimeters squared, that means each length of the duct is going to be 5 centimeters. So inside this kind of entry region of the duct, the boundary layer basically never gets higher than 2.5 centimeters. Okay? So in order to solve for L, you basically set delta 99 equal to 2.5 centimeters, and then you solve for X. Okay? And then part B, the logic is kind of the same thing, where you basically want to make it such that the middle of the duct is basically kind of exactly where the edge of the boundary layer is. Okay? And then for CD, you basically use the same equation, but you change the free stream speed. Okay, so that's going to change your answers. Okay. Part D, I basically wanted to ask you when the boundary layer goes turbulent. So there was a certain point where the Reynolds number crosses a certain threshold. So I want you to find the distance for that. And then part E, basically, I wanted you to use the formula for the friction coefficient for the boundary layer, and then use that to compute the friction force. Okay? So it's all kind of based on, there's kind of one page in the notes with kind of all these formulas, and kind of was based on that. Okay? So for boundary layers, because we did a lot of the stuff was conceptual and theoretical, this was kind of something kind of based on the Blasius boundary layer that I wanted to give you guys kind of practice with the equations. Okay? So what we're going to do today is we're going to learn about the momentum integral equation. Okay, and then that will allow us to kind of do more stuff with boundary layers, more than just kind of the theoretical stuff. Okay, so that hopefully that helped you out for problem 3. So there was another question on, are you going to provide guidance for midterm 2? So yes. So for midterm 2, I'm going to give you a study guide as well. So then you'll have that for that. Okay, so the question is, the Blasius boundary layer is for a flat plate, not a duct. So you're correct. So that boundary layer, the equations for a flat plate, but a duct, you can kind of basically assume that you have flat plates kind of above and below, kind of all the sides like that. Yeah, so it's kind of like 4 flat plates kind of all kind of around each other like that. Yeah. Let me pull up the notes again. All right. Any more questions? Just either on the homeworks or just logistically before we get started today. Okay. And feel free to use your microphones too. So if you want to unmute yourself and just kind of cut in with the question, that's fine too. But if you want to just use the chat, that's okay. But so either way is okay. So I have my headphones in, so I have the audio. So whichever way is more comfortable for you, then you can use. Okay, so when we left off last week, we were discussing boundary layer separation. Okay. So what we said was boundary layer separation. What that was that, you know, if you have some curved body like this, right, you have your boundary layer that's attached. At some point, what happens often is that the boundary layer will actually detach from the body. Okay. And what it means when the boundary layer detaches is that behind your solid body, what you have is a wake. Okay. So a lot of times, especially in basically for cars and for planes, you want to avoid this as much as possible, because a wake basically means that you're going to be working pretty hard to kind of overcome the pressure difference in that wake. Okay. So basically, what we kind of the last thing that we covered last week was that the kind of one of the biggest deciding factors on whether a boundary layer separates or not is the pressure gradient at the surface. Okay, or dpdx. Okay. So depending on the sign of the pressure gradient, this will kind of help us define what the boundary layer is going to do. Okay. So last time we did dpdx was less than 0. Okay. So when dpdx is less than 0, that means this is a favorable pressure gradient. So for favorable pressure gradients, this is good because what this means is the flow is going from high pressure to low pressure. So in those situations, then the boundary layer tends to stay attached to the body. Okay. So when dpdx is greater than 0, that means the flow is going from low pressure to high pressure, right? So you can think of this as basically you're trying to push like a boulder kind of from the bottom of the hill to the top, right? So that takes a lot of work. So when the dpdx is greater than 0, then we say that this is an adverse pressure gradient. Okay. And so what tends to happen in an adverse pressure gradient is that this will form an inflection point in the velocity. So an inflection point, what that basically means is that, you know, usually our velocity profile looks something like this. Okay. So this is for a nice healthy boundary layer where we basically have a high velocity gradient here. Right. So for an inflection point, what that means is that the velocity gradient tends to have kind of something that looks like this. But right here, this is an inflection point. Okay. So inflection points are pretty bad because this basically tells us that the velocity gradient is going to be 0 at the wall, and if the velocity gradient is 0, that means the viscous stress is also going to be 0. So when there's going to be 0 shear stress and 0 velocity gradient, this is basically the point at which the boundary layer separates. Okay? right. Any questions on this before I wipe the board? Okay. Okay. So basically, you want to avoid, or basically, whenever you have an adverse pressure gradient, that's usually a bad thing for boundary layers. Okay. So that kind of begs the question, what causes the pressure gradient to be favorable and what causes it to be adverse? Right? So actually, the biggest determining factor for the pressure gradient in boundary layers is actually the geometry. Okay. So it's hard to kind of talk about this or kind of specifics for it because geometry can very quickly get very complex, especially when you're looking at complex vehicles like your car or maybe like an airplane. Okay? But I can give you at least some heuristics or some qualitative things that you can look out for. So basically, the kinds of geometries that kind of encourage kind of adverse pressure gradients are geometries with kind of sharp changes. Okay. And kind of the opposite of that is if you have a kind of a smooth geometry, then this will help the boundary layer to stay attached. Okay. So if you know anything about sports cars, so if you look at things like a Lamborghini, you should see those geometries are very, very smooth, right? So they're basically kind of hugging the ground, and you barely have kind of sharp changes. So that design is not only does it look really nice, but it's also to kind of discourage this boundary layer separation. Okay. You contrast that with I forgot what it is, but basically it looks like you're driving a box around. Okay? No disrespect if you're driving that. A lot of my good friends drive that, but sometimes I just like to tease them about it. But because of that kind of very blocky geometry, the aerodynamics on that are pretty terrible, and so you're going to have a lot of adverse pressure gradients and boundary layer separation. Okay? So we can kind of just classify those two classes of geometries. Okay. So for something like a Lamborghini Tesla truck, yeah, the Tesla truck. Apparently, the Tesla truck has very good aerodynamics, but I'm not sure I believe that. But for something like a Tesla truck, or something like a regular truck, we call that a blunt body. Okay. So my blunt body here, I'm just drawing a circle. Okay. So for a circle, you have relatively sharp changes kind of on the tail end right here, okay? And that'll cause the boundary layer to separate. Okay? And then opposite of this, we have bodies which we call streamlined. Okay? So these are geometries that people kind of generally associate with being aerodynamic, and the reason for that is because you have kind of very smooth changes here on the back side. Okay? So that'll really help your boundary layer stay attached as long as possible. Okay? So then that kind of really minimizes the effect of the adverse pressure gradient. Okay. So that's all that. That was kind of the last bit of the lecture notes that we kind of didn't finish last time. So are there any questions on that before we move on to this set of lecture notes on boundary layers? Okay. Yes. Sure. So the question is, can we go over the inflection points again? Okay. So by inflection points, that's kind of like a math term for basically when the gradient is equal to 0. Okay. Okay. So kind of the figure that kind of goes along with it looks something like this. Okay. So we have our velocity distribution. So kind of schematically, the inflection point kind of looks something like that. Okay. So you basically kind of like a flat kind of region at the beginning, because the normal kind of healthy boundary layer looks something like this, right? Where you have kind of a sharp gradient right here. So as the kind of adverse pressure gradient acts on the velocity for a while, then what that does is it creates kind of an inflection point at right here, okay? Where the gradient of u is 0 right here. So when the gradient of u is 0, that means the viscous stress is going to be 0, and at that point the boundary layer just kind of separates from the body. Any more questions on this? All right, so let's move on. Okay, so this is kind of part 2 of the boundary layer notes. Okay, in particular, this is the notes that are going to be on integral equations. All right. So last time when we did boundary layers, we basically worked on exact solutions. Right? Right, so we saw basically one example of this. So the example that we saw was the Blasi solution. Okay? So we did all that work for the Blasi solution. If you remember, in the end, we couldn't even solve it. Right? So we ended up with something that was that we had to solve numerically. Okay? So that was kind of a little bit disappointing, right? Because we did a lot of work and we got something we couldn't solve. But remember, kind of the goal for that for exact solutions is that what we're solving for is the velocity distribution. So in other words, we were solving for u and for v, kind of related. Okay. So it turns out for boundary layers, a lot of times for solving for the full velocity distribution, this is a little bit overkill because a lot of times, that's a little bit too much information. I mean, it's useful if we can grab it because you can kind of derive a lot of things from it. But a lot of times, we don't have to do all that work to get the full velocity solution. Okay. So what's kind of practically more useful are some of the other metrics that we talked about last time. So some of those things being like the boundary layer thickness, right? Things like the wall shear stress. Okay. And then, like we just talked about, whether the boundary layer separates or not. Okay. So these are all things that you can get eventually from the full velocity solution. But that kind of begs the question: is there kind of an easier way to get at these things without having to go through and solve for the velocities, which takes some kind of really long, involved process, or even worse, some numerics? Is there a better way to do this? So it turns out that there is. Okay. And the way that we're going to get it is we're going to take our boundary layer equations and then integrate them. And then by integrating, basically a lot of the quantities like the momentum thickness and the wall shear stress will kind of naturally come out, and it'll be a situation that will be like easier to solve than the velocity solution. Okay, so let's go ahead and get started with that. So kind of the first place that we'll start is a kind of a method developed by a guy named von Karman. So we put his name on this, right? So these are the von Karman momentum integral equations, or equation. And so just like we talked about up there, basically what we're going to do is we're going to take our boundary layer equations and then integrate that, okay? So just to remind you, here are our boundary layer equations. So they consist of both conservation of mass and conservation of momentum for a boundary layer, okay? So conservation of mass, we have our continuity equations. We have du dx plus dv dy is equal to 0. And we have our momentum. Okay, so our momentum looks like this. Okay, so you have u du dx plus v du dy is equal to ue du e dx, where ue, remember that's the free stream velocity, okay, plus our viscous term, which is 1 over rho d dy of mu du dy. Okay, where ue, this is the free stream velocity. Okay. So I put the boundary layer equations in this form, where this guy right here, this guy is our wall shear stress, or just shear stress. Okay. So then what we're going to do is we're going to work on these equations and then eventually integrate them. And then what's going to come out is something that's, you know, a little bit easier to work with than the velocity solution. Okay. All right. Any questions on this before I wipe the board? Yes. Yeah. So this viscous shear, that's going to be tau. Yeah. So that's exactly what we're going to put in there. Mm-hmm. Okay, so let me wipe the board. We'll keep going. Okay. Okay. So the way that this starts is that we, we're going to do something a little bit weird first. So we're going to take our continuity equation. Okay. And then what we're going to do is we're going to multiply this by u. Okay. Okay. So on the right-hand side, we still get 0. Okay. And on the left-hand side, we get u du dx plus u dv dy is equal to 0. Okay. And so what we're going to do, since this is equal to 0, is we're going to take this and add it to our momentum equation. Okay. And so what we do, or what we get from that is this. So we get u du dx plus u dv dy. So all that just came from up there. And then now we have the contributions from our momentum term. So we have u du dx again, plus v du dy. Okay. And then this is equal to everything on the right. So we have UE dUE dx plus 1 over rho d tau dy. Okay, where I've replaced the viscous shear with tau, kind of just like as we talked about. Okay. Okay. So that's kind of the first step. Okay. So next, let's simplify the left-hand side. So on the left-hand side, we have this term and this term. They're exactly the same. So they're going to become 2u du dx, right, plus u d v dy plus v du dy, okay, is equal to, the right is still the same, okay. So the right is still ue due dx plus 1 over rho d tau dy, okay. And so what I'm going to do here is I'm going to take this term, and what I'm noticing is that this is kind of like the reverse. We're going to do like a reverse chain rule. Okay, so this is going to be the same as d dx of u squared. Okay, and then if we do kind of the reverse chain rule on this guy, what we get is d dy of u v. Okay. Okay, and the right-hand side still stays the same. Okay. Right. So the question is, how are we able to add the momentum and continuity together? So that's a good question. So remember, the continuity equation is du dx plus dv dy is equal to 0. Okay. So because everything here is equal to 0, right? We can add them together because it's basically like we're adding 0 to our momentum equation, right? So actually, if we want to simplify this step, this part right here, since that came from continuity, this is actually equal to 0. Right? So we can add it together because we're basically just adding 0 to the equation. But by adding 0 and by adding kind of these terms together, this kind of gets us to a form right here, which will kind of be useful for us once we do the integration. Yep. Any other questions on this? Yeah, the adding 0 trick is kind of something that's abused kind of a lot in applied physics and math. So it's not, a lot of times it's not as well explained, but that's basically what it is. So kind of its close cousin is multiplying by 1. So you can take something and you multiply by like u over u, right? So in the end, you don't change anything because u over u is equals to 1. But sometimes that lets you rearrange some terms to make things simple. But yeah, these are just kind of silly math tricks that kind of help in proofs like this. Okay. So then now that we have that, let's integrate this. Okay. So in particular, we're going to integrate this in terms of y. Okay. And then we're going to integrate from y is equal to 0. Where y is equal to 0, this is going to be our surface, right? And then we're going to integrate to y is equal to infinity, which is just somewhere really, really far away. Okay. Okay. And so what we're going to do, so let's do that for this equation. And then at a certain point, we're going to need to kind of take a little pit stop to kind of evaluate one of the terms. Okay. So I'm going to wipe this board and basically perform that integration. Okay. Okay. So we perform that integration. We have integral from 0 to infinity of d dx of u squared dy. Okay. Plus integral from 0 to infinity of d dy of uv dy, okay? And then that's going to be equal to integral from 0 to infinity of ue due dx dy plus integral from 0 to infinity of 1 over rho d tau dy dy. Okay. All right. So here things are going to get a little bit tricky, so it's kind of important to pay attention to the details because all of these integrals are with respect to dy. Okay. So for the integrals where we have a derivative with respect to y, what this will do is it'll allow us to basically evaluate this really simply. But for the terms where we have dx on the denominator, we need to be careful here because the dx won't be able to cancel out. Okay, so let's do these integrals first. So let's do this one, right? So this basically just turns into the integral of du v, right? Because this dy is going to cancel out with this dy right here. Okay, so what this is equal to is u0 v0, or sorry, u infinity v infinity minus u0 v0. Okay, where u infinity v infinity, that's the value of the vertical and horizontal velocities really far away from the boundary layer, and then u0 v0, that's the values at the surface. Okay, right. And so we know that at the surface we have a no-slip boundary condition where the velocity has to equal 0. So then this guy cancels out. Okay. And then for this guy, we know what u infinity is. So u infinity is going to be ue. That's our free stream. So v infinity we actually don't know yet. So we actually we need something else to solve it. But we'll kind of table that for now and kind of bring it up later. Okay. So now let's do this integral right here. Right? So we have integral from 0 to infinity of 1 over rho d tau dy dy. Okay. Just like up there, the dy's are going to cancel out. So we have 1 over rho tau at infinity minus tau at 0. Okay. So one assumption that we'll make is that far away from the plate or far away from the surface, we're going to have no shear stress. Okay. Okay. And that's kind of supported by the fact that, remember, we have this whole inner and outer solution. So in the outer solution, remember, viscous effects are very negligible. So outside the boundary layer, basically no viscous effects are going to be there. So we can basically say that's going to be 0. Okay. And then this tau 0 right here, this is the viscous shear stress at the wall. Okay. And if you remember, from our Blasi solution, finding out the viscous shear stress at the surface, this is something that's really important. So, we're still kind of have a ways to go, but we can see that, we've already have something that's going to be really useful to us in practice. Okay. All right, any questions on these two integrals? Okay. So before we do the integrals with the x derivatives, let's work on this first, okay? Because we need an expression basically for v infinity. Okay. All right, so I'm going to wipe the board. Okay. So to find v infinity, what we're going to need to do is we need help from the continuity equation again. Okay. So let's take our continuity equations. We have du dx plus dv dy. Okay. And then just like we did for the momentum, let's integrate this from 0 to infinity. Okay. And all this is equal to 0. So the integral of 0 is just still going to be 0. Okay. So let's break this up. So the first term, we have integral from 0 to infinity, du dx dy. Okay. So we don't know what to do with that yet, but this is going to be equal to minus integral from 0 to infinity dv dy dy. Okay. Right. And so just like we saw before, when we have this matching derivative here, we can cancel that out. Okay. So what we say is the integral from 0 to infinity of du dx dy. Okay. Oh, question. So why is there a double 0 at the first equation? Oh, so I basically have this double 0 right here, basically just to say that our continuity equation is still going to be 0. So when we take the integral of 0, we still get 0. That's basically all I just wanted to say. So on the right hand side is still going to be 0. Okay. So on the right hand side here we have minus v infinity minus v0. Okay. And since we know that v0 is equal to 0 due to no slip, we finally have an expression for v infinity. So v infinity is going to be minus integral from 0 to infinity of du dx dy. Okay. So we can use this basically expression in the previous equation before. Okay. Right. All right. Any questions on this? Okay. So if we kind of go back to our original momentum equation where we did the integral, let's work on a specific term, and that was the u infinity term. Okay. Actually, hang on. Let me kind of, so I did stuff a little bit out of order on my notes. Let me kind of just reorient myself. Okay. So actually, wait, let's take that result. So let's plug in. Okay. So let's plug in for v infinity. Okay. So then what we get from that is d dx integral from 0 to infinity u squared dy. Okay. So that was the first term that came out of our momentum integral. Okay. Minus integral from 0 to infinity of ue due dx dy. Okay. So that was the other term that came out. Right. Okay. And then this is equal minus ue times, and this was times ve, or v infinity, so we can plug in for that. So this can be u integral from 0 to infinity du dx times dy. Okay. And on the right hand side we have minus tau 0 over rho. Okay. And that was the wall shear stress. Okay. Okay. All right. So now let's look at this person. Okay. So remember, this term was the result of plugging in for v infinity, right? So this came out of the first integral where we had ue times v infinity, and then now we plug in for v infinity, and let's look at that term. Okay. So with that term, we're gonna do like kind of a reverse product rule. So this is where I kind of wave my hands a little bit and do a little bit of magic, and that's when you're supposed to kind of believe me that this is right. Okay. So let's take a look at something that looks like this. So we have d dx of the quantity of ue integral from 0 to infinity of u dy. Okay. So here we have to use basically the product rule for both of these. So this can be equal to du e dx integral from 0 to infinity of u dy, okay, plus ue integral from 0 to infinity of du dx dy. Okay. If we solve for this term right here from this equation, then we get ue integral from 0 to infinity of du dx dy is equal to d dx of the whole quantity ue integral from 0 to infinity of u dy minus due dx integral from 0 to infinity of u dy. Okay. And so what we're going to do is we're going to take this quantity right here, okay, and then plug that in for this guy right here. Okay. So you're probably wondering, why are we doing this? So this is kind of where I wave my hands to say that this will kind of make things better. Because ultimately where we're going with this is that we're going to put this we want this in terms of things like the momentum thickness, the displacement thickness, and the wall shear stress. Right? So the question is that last part u dy? Yes. So this last quantity right here is u dy. Okay. Okay. So any questions on this? Sorry, I know it's a little bit kind of a bojangled a little bit, but we're getting to the part where it's where things will be a little bit more clear. So the question is, will we ever have to do a reverse product rule? On the exam, no. So this is kind of a feature that's kind of unique to this proof. Yeah. So basically, what we're doing is we're kind of deriving the momentum integral equation. So I won't ask you guys to do a derivation or a proof on an exam. So this is not something that you'd have to do. But it's just kind of for me to kind of show you where each of the terms kind of come from. Yeah. Okay. So let me clear this board. Right. So if you plug that back in and you kind of combine some terms together, you'll get something that looks like this, right? Right. So you get d dx of integral from 0 to infinity of u squared minus u infinity, or ue, sorry, u dy, okay, plus due dx integral from 0 to infinity of u minus u infinity dy, okay, is equal to minus 1 over rho tau 0, okay. So we're almost there. And so what we're going to do for this term is we're going to factor out u infinity, or ue, okay. And then this integral right here, we're going to factor out ue, okay. So then we do that, then we get d dx of integral from 0 to infinity of ue times 1 minus u over ue dy plus ue due dx integral from 0 to infinity of 1 minus u over ue dy is equal to 1 over rho tau 0. Okay. All right. So one more step. We're going to take this and factor out UE, okay, squared. So then what that gives us is d dx of UE squared times integral from 0 to infinity of U over UE times 1 minus U over UE dy, okay, plus UE dUE dx times integral from 1 minus UE dy, 0 to infinity, okay, is equal to 1 over rho tau 0, okay? So it looks like a mess, partially just because my handwriting on the handwriting on my iPad is really terrible, right? But I kind of want to draw your attention to these integrals here, okay? So if you remember kind of at the very beginning of last week, we went over different definitions for the thickness of the boundary layer, okay? And so this expression right here, kind of after all this work, this is our momentum thickness. Right? And this right here, this is our displacement thickness, delta star, okay? And so what we can do is we can plug in for these and basically vastly kind of simplify this equation, okay? All right. So let me kind of erase up here and I'll kind of write out the von Karman momentum integral equation. Okay, so the von Karman integral equation looks like this. We have d dx of UE squared times theta, where theta is our momentum thickness, right? Times UE dUE dx times delta star, where delta star, that's our displacement thickness, right? Is equal to tau naught over rho. Okay. So this right here is the von Karman momentum integral equation. So you can see it's a much simpler equation that we can solve for theta, delta star, and tau. Okay. So the unknowns in this are going to be these guys right here. Okay. So it's one equation, but we have three unknowns. So actually, by itself, we can't use it to solve problems. But if we combine this together with some experimental measurements, we can actually solve this in a much more easily than the Blasius solution. Okay. All right. Any questions on this before we move on to the next thing? I know that derivation was a little bit messy, and I apologize for that. But this was kind of the result that I was hoping to get to. So we have just one equation, and those integrals kind of became the thicknesses of our boundary layer. Okay. Okay, so then now how do we go about solving this? Okay, so there's been a lot of research on how to solve this equation, but one method that's relatively simple is called Thwaites method. Okay. So what Thwaites said was that because that previous equation was one equation and three unknowns, we needed more basically equations to solve for this. Okay. So what Thwaites basically did was he ran a bunch of experiments, and he basically found ways to use the previous equation along with his experimental results in order to solve this equation more simply. Okay. So in particular, he has these two kind of correlation equations or correlation functions. Okay. So the first function looks like this. So he says that tau naught, which is one of the unknowns in our von Karman integral equation, this is equal to the viscosity mu times UE all over theta, which is our momentum thickness, times L of lambda. And so in this equation, what we're basically relating is tau, which is our wall shear stress, and theta, which is our momentum thickness. Okay. And then this new person that came into the equation, this guy, this is what's called the shear correlation. So this shear correlation, this is what I meant was this was based on experimental measurements. So basically there's a table which I've uploaded onto Titanium, which you can use to basically evaluate this L. Okay. So this is tabulated. Okay. And so you're probably wondering what's that lambda is in there. Okay. So this L, the shear correlation, is a function of lambda. So lambda is given by this. And this lambda is often called the correlation parameter. Okay. Okay. So that's one equation there, right? One equation with a correlation parameter. So now we need another equation. So the other equation that Thwaites came up with looked like this. So it basically relates the displacement thickness and the momentum thickness. Okay. So the other equation that Thwaites came up with was he said that the ratio of the displacement thickness delta star over the momentum thickness theta is equal to some function h of lambda. Okay. Where this h of lambda, this is often called the shape factor. Okay. And then just like the shear correlation, this was based on experimental measurements. So you can look up values for these in a table. So basically, we can use these equations and this correlation parameter together with the von Karman integral equation and solve for theta, delta star, and tau. Okay. All right. Any questions on this before I wipe the board? Okay. Okay. So for this, so for the rest of Thwaites method, I kind of skipped the derivation for you, but you can imagine we basically plugged in all those quantities back into the von Karman momentum equation, okay? And then what you get in the end is kind of an explicit equation for the momentum thickness. So what Thwaites found was that theta star is equal to 0.45 nu over ue to the 6th power, okay? And this is often a function of x. And then we take the integral from 0 to x of ue to the 5th power of x dx, right? Plus theta naught squared uo squared, right? All divided by ue to the 6th. Okay. Oh, sorry, this is a 6th power right here. Okay. And let's define some of these new variables, okay? So theta naught, this is the momentum thickness at x is equal to 0. Okay. And then u0, this is the free stream velocity. At x is equal to 0, okay? All right. So this equation, along with kind of the equations that were on the last board, basically comprise Thwaites method, okay? So if you want to solve boundary layer equations using Thwaites, kind of the recipe is kind of always the same. Okay. And so the recipe is to use this equation right here. Okay. So since through Thwaites method we get an explicit formula for the momentum thickness, we can solve for that kind of outright. Okay. Then once we have the momentum thickness, we can use the equations on the previous page to solve for either delta star or tau naught. Okay. So there's one other nice feature to Thwaites method that we can use. Often, we're often interested to see, if the boundary layer is ever going to separate from our surface, right? So Thwaites method actually gives us a way to either confirm or deny that boundary separation is going to take place. Okay. Okay. And the way that you do that is you compute lambda, where lambda, remember, that's our correlation parameter for Thwaites method. Okay. And if lambda ever reaches a point where it's less than minus 0.09, right, then boundary layer separation will occur. Right. So we'll see kind of, I have a couple examples that kind of shows this in action. Okay. All right, any questions on this before we jump into a couple examples? Okay, so let's do a couple examples then. All right. So first example that we're going to do is we're going to take our Blasius boundary layer, and then we're going to use Thwaites method to kind of confirm all the equations that we found before. Okay. It's a funky E. All right, so in this example, we're going to use Thwaites method. For a boundary layer over a flat plate. Okay. So there's our flat plate. There's our velocity coming in, right? And then there's our boundary layer, okay? Okay. So let's start using Thwaites method, okay? So first, let's compute theta, okay? Remember, that's always the first thing we do is we compute theta. Okay. So in this case, since we have a leading edge, which is probably the most common thing, we say that the momentum thickness starts out at 0. So what this means is that theta naught is equal to 0. Okay. And then we also know, because of the flat plate geometry, that our free stream velocity, UE, is a constant. Okay. So let's take that information and plug it in. Okay. So we have theta squared is equal to 0.45 nu all over UE, right, to the 6th times integral from 0 to x of UE to the 5th dx, okay, where this is a constant, right? Then we have theta naught squared, UE, or U0 to the 6th, and UE to the 6th, okay? And so since the boundary layer starts out with 0 thickness, right, this term goes away, okay? So then if we plug in, you know, for everything, we get theta squared is equal to 0.45 nu x all over UE. Okay. So basically perform that integral from 0 to x, and we get x that comes out of there, right? So then if we take the square root, we get theta is equal to 0.671 square root of nu x all over U infinity, okay, UE. Okay. So if you compare this to the solution that we got from the Blasius solution last time, you see that this is really close. So we went about it in a kind of a very different way, but we got something that was, you know, basically the same thing. So this kind of shows that Thwaites method is, you know, something that's pretty reliable. Okay. All right. Any questions on this part? Okay. Okay. So now let's compute the displacement thickness. Okay. Okay. So for the displacement thickness, we're going to use the function that involves the shape correlation. Okay. So we have delta star all over theta is equal to h of lambda. Okay. So we have theta. So that's what we just computed in the last part. Okay. So now let's evaluate this h of lambda. Okay. So the first thing we need in order to compute h of lambda is we need to know what lambda is. Right? So lambda is going to be theta squared all over nu times due dx. Okay. So we have the momentum thickness squared divided by the viscosity times the derivative of UE. Okay. And so since UE is a constant, we know that this term is going to go away. Okay. Okay. So if we solve for this, we get delta star is equal to theta h of 0. Okay. So if we look this up in a table, the table that I gave you online, okay, and then what you'll get is 1.75 times square root of nu x divided by UE. Okay. And you can see that this is pretty dang close to what we got last time as well. Okay. Right. So then finally we have the wall shear stress. Okay. And for that we're going to use the other formula. So we have tau naught is equal to nu UE over theta times L of lambda, right? Where lambda we know is going to be equal to 0. So if we plug everything in, we plug in our expression for theta, we know UE, we know viscosity, and we can look this up in a table. Right. What we get is 0.328 times mu UE to the 5/2 times 1 over square root of nu times x. Okay. If you compare this to the Blasius solution, this is also something that's pretty close. Okay. Okay. So this was kind of a very straightforward example. Basically, we're applying the Thwaites method to something that we already know. So the next example, we're going to apply it to something that's a little bit more practical. Okay. So since we're almost out of time, I'll probably start the example, and then we'll probably pick it up kind of first thing after spring break. Okay. Are there any questions on this example before we cut it off? Okay. So I'm going to clear the board. Okay. Okay. So then let's do the next example. Where we start it. Okay. So in this example, we have a diffuser. Okay. So a diffuser, it's a device which is used to basically reduce the velocity in a stream. Okay. So in particular, this diffuser is designed to reduce the velocity by half. Okay. The question is it the opposite of a nozzle? Yeah. Yeah. So the diffuser is basically a nozzle that's backwards. Yeah. So the kind of geometry looks like this. Okay. So on the left side here, we have velocity that's coming in. So we'll call this UE. Okay. Right. And on the outlet here, we have UE divided by 2. Okay. And then we say the length of this diffuser is given by L. Right. All right. So this is kind of it'll be a little bit different than our homework case. So in our homework case, we had the boundary layers being so big that they kind of overcome or they become basically on the same size as this. In this case, we're assuming that the boundary layer is going to be really small, such that they stay kind of pretty confined to the walls. Okay. So the boundary layers are going to be there, and they're going to be important, but they're not going to affect the overall flow. Okay. And so what we want to do is we want to use Thwaites method. And we want to use it to determine if the boundary layer is ever going to separate in this diffuser. Okay. Okay. All right, so I'll probably leave it at that. So if you want to look at the rest of the details of the example, they're in the notes that's posted online. But I think we're out of time today, so I'll leave this here. So the next time I'll see you guys will be after spring break. So have a great spring break. Rest up well. Please stay safe. Please stay healthy. Kind of like what everyone's saying. Don't go outside if you don't need it, and wash your hands constantly. Okay. Yes, stay home. Right. So the question is, will you be posting these notes before we complete? So the notes are already posted. So I'm going to be working on the next lecture notes, and I'll basically posting them basically as I do them. Yeah. Yeah. So the first thing that we're going to do after spring break is going to be vorticity. So I was working on that a little bit today. And as soon as those I finish that, that's going to be up on Titanium. But these notes should already be up there, so you can view them. All right, thanks guys. Yeah, have a great break. I will see you guys after spring break. Yeah, stay safe, everyone. All right, I'll stick around for a little bit if you have any more questions. But if you don't have questions, then feel free to leave the Zoom. Yeah, as soon as as soon as I leave this, I'm gonna post the recording onto YouTube. A couple people still, but my cat is hungry. No, she doesn't. She doesn't like to be locked in a room, that's for sure. Thanks, everybody. Yeah, they have litter. All right, so if there's no more questions, I'm going to end the meeting. So if you have any questions, definitely you can send me an email. So I'll be having my regular office hours next week, even though it's spring break. So I'll just have it through Zoom. I think that's kind of a nice thing. And then, so besides that, I will see you guys after spring break. Bye, everybody.